Hello everyone. In this video I will talk about a Python based DeepChem library which you can use if you are doing any project in sciences. So a little bit about it. As it says, it aims to provide high quality open source software for scientific machine learning. So in general what it does is, let's say in chemistry we have different molecules, right? Like let's say phenol and these type of molecules. So let's say we have a list of 500 800,000 molecules, and what we generally do is we convert them into smile strings, right? And then into descriptors, molecular descriptors or fingerprints, uh, graphs, right? So we use for that we use rdkit and pytorch for graphs, modred, paddle. So these type of software or libraries for generating these descriptors or featureizing smiles, and then we just build models using different softwares like uh, again pytorch, dgl for graphs, and scikit-learn for other general purpose models like random forest, linear regression and stuff. So what DeepChem Kit does is, if you have these smile strings, you can do all that. You can build a model just with this library. So it is based on PyTorch. And so what is DeepChem? It is a Python library for machine learning and deep learning on molecular and quantum datasets. It is built on top of PyTorch and other popular machine learning framework. So you can read more about that. There is short tutorials about it, and a link to the Google Colab notebook. You can there is a forum. If you have any questions, you can just ask here. You can discuss docs. Basically this is the thorough explanation about this library, and there is a book as well, and there is a GitHub page. So in this video I will practically show you how you can build models using and featureize smile strings using DeepChem. So what we are gonna do is, yeah, there is one more thing, molecular net. Molecular net is basically a DeepChem library or a cloud space which DeepChem has, and it houses all the data sets. So this is the cheat sheet. These are the names of the data sets. Base for regression problem. It has a description, provide binding energy results for sets of inhibitor type molecules, data points. It has a reference as well. So there are many different types of data sets which you can use for practice or even for research purpose. And in this video I'm going to be using this free solve dataset. It's a collection of experimental and calculated hydration free energies for small molecules in water. So list of molecules 643 smile strings. This is the reference. So let me just go to molecular net, and here datasets. If you just click on free solve, it will be downloaded. So I already have it downloaded, and I have uploaded it on Google Colab notebook. Its name is sampl.csv file. And now in order to run DeepChem you need to install PyTorch, DGL and all these libraries, and make sure you use these versions, because the other new versions could be non-compatible with the DeepChem version that you're using. So let's just quickly install these and import all these libraries. It will take some time, so let's just wait for it to finish. Okay, so we have finished installing and importing libraries. Now my dataset is here, so let's read this. This is the first 5 data points. It has IUPAC name, smiles, experimental and calculated free solvation energy. So we just need the experimental values and smile strings. And what I'm gonna do here is I'm gonna train test split using sklearn, and I will tell you later the reason for that. So let's just first split it into train and test split. So I'm using train test split from sklearn.model selection. So 20% is test and the rest is training. So you can see we have a shape of 642 and 80% of it would be 513. So train shape is 513 and test is 129. So let's reset the index and join it again. Now I have kind of concatenated it along the rows. So basically the first 513 yeah 513 data points are of that of train and the remaining are that of test, so keep that in mind. Now let's just rename the column experimental, which is our target, to task 1. Okay, so now basically we are loading a custom data set, right, which we have downloaded on our computer. So for that, all you need to do is just use this code here. What it will do is convert this data frame into a temporary file, and it will load this temporary file, and we have already changed the name of the target to task 1. So this is task 1, which is our target, and feature field is smiles, right? So feature field is smiles. Now here we need to provide the featureizer. Featureizer is basically we are telling DeepChem to convert these smiles into here convolution molecular featureizer, so into graph, and we need to mention what type of featureizer we need to add here. So if we go to the DeepChem documentation, here we have featureizers. So you can see we have convolution molecular featureizer. This class implements the featureization to implement this particular graph convolution. So basically this is different from the V featureizer, and of course that is gonna be different from molecular GAN featureizer. So different type of models like attention FP or graph convolution networks, these require different type of featureization. So you make sure whatever model you are using is compatible with the featureizer that you are using initially. So here I am using just very simple convolution molecular featureizer, and you can go ahead and read more about it in the documentation. So after we have instantiated it, so we'll be saving our dataset into a dataset variable using this class dataset method. And let's just run this. So length of the dataset is 642. If we look at the type, so it's a DeepChem object, right? So we have converted it into a kind of DeepChem object. Now if you want, you can further explore your dataset. So if you want to see IDs or smile strings of first 10 molecules, you can just use .id. So these are the smile strings of the first 10 molecules, or if you want to see all of these, that would be a long list. So basically let's just restrict it to first 10. And if you want to see the shape, you can just use .get_shape method. So so it has 4 things, right? So what we have is X, Y, W, and ID. X is our graph, Y is our target, W are the weights, and IDs are the smiles. So you can just print all of these here. I'm just printing Y and ID. So the target value corresponding to the first molecule here, or first smiles, is this, for the second is this. So you can just print out information if you want. So let me just comment this one out, and yeah. Next, again, if you want to see the X here, so let's just first see what X is. Dataset.x. X is a graph. So these are the graph objects of all the molecules. And if you want to see just for the single molecule, so this is the graph object. And if you want to see the features, just use get_atoms_features method. So this is how the graph representation of the first molecule looks like. So you can explore further using this command. Now it's time to split our data set, right? So what we have now is, so we had the smile strings and we had converted it into graphs already, right? Now what we need to do is, we have a data set of 642 molecules, right? And it has graphs and y is the target. Now we have 642 data points. We wanna split it into train and test set, test and train, right? Now in DeepChem you can use various type of splitters. Now there is a particular splitter called specified splitter. So there is a reason I first split it into train and test split, because let's say you already have train and test split already. You know, okay, this is my training data and this is my test data. And when you have converted into DeepChem object, which is data set, right? Now you can just use this specified splitter to split it according to the index ranges. For example, I'm gonna be using this specified splitter, so let me just go ahead here in the splitters, in the documentation, in the specified splitter. So splits data in the fashion specified by the user. So we are gonna be using the index range here. For example, here now this is a class, and what we are gonna be putting the parameters in is validation indexes, if you want to split it into validation set as well, and test indices. So these are the index values, right? So let's just go back here. Now I had already told you when we concatenated it in here, the first 513 are gonna be train data points and the rest are gonna be the test. So basically we need to input here the test range, and which is 513 to 642. So we are gonna be instantiating it, and then we are gonna be saving our train and test dataset as train underscore dataset and test underscore dataset, and we are gonna be calling this method on this dataset. So let's run this. Now if you look at the length of train dataset, it is 513, and for the test it is 129, right? Now we have basically, so we have done the train test split according to the index number, right? Index range, because we already knew our train and test set. Now we have train and test data, and what we can do is build a model. But you need to make sure that you have used this convolution molecular featurizer, and you need to see which model, basically graph model, takes input as this featurizer. So let's just go back to the documentation here. Now we want to build model, right? So let's go to model classes. So this is kind of the cheat sheet. You can see here, this is the model name, reference, classifier. It will tell you whether you can use it for classification or regression. We are using it for regression, and acceptable features, right? So circular fingerprints, RDKit. So we don't really see convolution molecular featurizer for this type of thing, right? So we need to kind of search for it. And if you go down here, this is particularly for molecules, the one which we are using. So here, convolution molecular featurizer, a DAG model is we can use, or what, graph convolution model, right? So for if you want to use this particular one, which is based on DGL and PyTorch, you need to use this featurizer, molecular graph convolution featurizer. So you want to make sure that you are using the compatible featurizer with the model that you want to use. So right now we are using this one. So let's just go ahead and build our model using this graph convolution model. And again, there is a reference for that. You can go ahead and read more about that. So model dc dot models dot graph convolution model, number of tasks, basically how many targets you have. We just are dealing with regression problem, so our task is one. So mode is regression, right? Dropout rate, this is a hyperparameter. 0.2 batch normalization false. And again, if you go here, if you yeah, graph convolution model. Yeah, so this is the model that we are using. It's a class graph convolution model, and if you can see here, it takes in parameters as number of tasks, graph convolution layers. So these are the hyperparameter. This is the default, and you can go ahead and change these as well. Dense layer 128, dropout rate default is 0. We are using 0.2. Mode you need to specify. We have specified regression, number of atom featureizer, number of class. So all these are hyperparameters, and you can play with these. And the information is in model classes. So let's just run this. So we have instantiated our model class, and let's fit our train data set, and you can change the number of epochs. I have used 100. You can just use according to your will. We have successfully built a model using train data set. Now, so we have built the model, right? Now we have a model. What we can do is we can test our test data set. So model dot predict our test data set values, right? So that would give us the predictions for test data set, and we already have the actual experimental value. So predicted and actual, we can get the metrics. So here, so now in order to predict, just use model.predict test underscore dataset for test prediction. So that would be y underscore pred. We already have the experimental values, right? So test dataset dot y was our, these are the actual values, and we can get the predicted values using model.predict. So I'm gonna be getting for both train and test. Let's just comment this one out. And again, if you want to see, you can just see the predictions. So these are the predictions, right? So now we need the metrics. We are familiar with R2 score, so I'm gonna be using sklearn R2 score method from sklearn.metrics. So R2 score y pred train and actual. So this is the actual, right? And similarly we can do for the test predictions, which we have done here, and the actual value. So it will print out the R2 scores here. So let's see how good the model is. So you can see here the train R2 score is 0.945 and the test R2 score is 0.866. So it's pretty good. Now this is the metrics from sklearn, right? They also have inbuilt metrics. So from this metric class, you can just use this dc.metrics.pearson R2 score. Now there is a little difference between R2 score and Pearson R2 score. R2 score basically measures how well a model explains the variance in the target, and Pearson R2 score, it is a linear correlation. It's a measure of linear correlation between the two values, predicted and actual. So there is a little difference here. So make sure you know the difference when you're reporting your values. So yeah, just model.evaluate here. Here we used model.predict. Here we are going to be using model.evaluate, and the input parameter would be train data set and metrics in this square brackets. So we are going to be doing for both train and test. Let's do that. So here we have the training and test Pearson R2 scores for our data. So yeah, just to keep the video short, I'm going to be talking more about DeepChem. Like there are several other ways: random split, scaffold split, all other splitters I'm going to be talking about, and other graph models also I'm going to be talking about in my next video. So stay tuned until then. Thank you for watching.